The 1929 Nobel Prize in Physics went to Louis de Broglie, whose real name and title was Prince Louis Victor Pierre Raymond de Broglie. Now, we'll get to all of that in just a second, but let's talk about what he did to win the prize. Remember, this is the early part of the 20th century, and quantum physics had evolved and was still evolving from the idea that energy is conveyed only in certain fixed amounts, or quantized amounts. Scientists had also figured out by this point that light can be both regarded as both waves and particles as it travels, because of these little things called photons. In 1924, Louis de Broglie introduced the idea that particles such as electrons could also be described not only as particles, but also as waves. That's right, light got its term to travel as a particle and a wave. Well, now the electron gets its shot. And it turns out he was right. This work was a bit contentious at the time, but was verified beyond any doubt by the way streams of electrons were reflected against crystals and spread through thin metal foils, or what we generally refer to in labs as thin films. The idea had amazing significance, and the proof had amazing significance, and it helped the continuation and evolution of quantum mechanics throughout this time period, which is something that still, in some respect, is still evolving today. It came from a famous aristocratic family of de Broglie, whose representatives for several centuries occupied important military and political posts in France. His father was a Louis Alphonse Victor, 5th Duc de Broglie. He was married to Pauline d'Amarelli, which I'm probably pronouncing that wrong, but that's okay. But she was the granddaughter of the Napoleonic general Philippe Paul. So he had come from a family that had an interesting history in it, as well as being a fantastic scientist. Now, when we started doing these videos, I promised I would try to show practical application wherever possible. So let's talk about what you use this wave-particle duality of electrons for. Well, there's a lot of different things, but one you've probably heard of is the electron microscope, because without this phenomena, it wouldn't work. So it does. We've had some fantastic pictures that come out of these things, all the way down to sort of the atomic scale, depending on how you think about it. But we've gotten some amazing work done with electron microscopes over the years. And more importantly, this wave-matter duality showed that we can now connect quantum mechanics with Newtonian mechanics, and we can make it so that those two things are not in contrast with one another. They actually fit in the same universe. And in fact, technically speaking, all matter does travel as a wave, just with wavelengths so absolutely long you couldn't possibly measure it, because it's just ridiculous. So you have to only measure the wavelength of very small things moving in very specific ways. So you measure it for protons and neutrons and electrons, but trying to measure it for a baseball would be very, very difficult. So it has led us to some wonderful things in the laboratory. It has led us to some other work in many different fields. But without this, the quantum world and the world that we walk through might have been different kinds of physics. This really does help, in an experimental way, verify that those two things understand and obey the same physics as one another. And that's what's really important, is we want physics to obey the same laws everywhere in the universe, not, well, it only occurs in these specific cases. No, physics is physics. It works everywhere, or it doesn't work at all. And this wave-matter duality really did help push some things together. So thank you for listening. Please don't forget to click subscribe and like. It does help us out with the YouTube algorithms. And we'll see you on the 1930 Nobel Prize, which is next.